here as part everyone, Pulka here as part of the series that Tutor Doctor is doing. We will be working on a couple of past papers, specifically in the chemistry section of physical sciences, and today we're going to specifically start with November 2017, and we will do question one, which is the multiple choice questions. We will do question two, which is the organic chemistry section, the general organic chemistry section. Question three, which incorporates chemical bonding into it, and question four, if we have time, which is the organic reactions section. So, without wasting too much time, let's get straight into it. And like I said, this is going to be on November 2017, chemistry paper 2. Start things off, the multiple choice section. This tends to be the most difficult section of the paper. So we'll take our time going through it. Okay, so a piece of advice just to start things off is you should always read the question twice. Once to understand which section you're working on, as this is the only question within the paper that will incorporate different concepts of chemistry, as well as a second time, then to kind of figure out what exactly they're asking so that you can answer the question. Now, question 1.1, most obviously organic chemistry. And they say the IUPAC name of an organic compound with this specific molecular formula is said to give one of these four options. So it's either heptanol, heptan 1 all, heptan 2 all, which are both alcohols, or heptanoic acid, which is a carboxylic acid. Now, if you look at this, you can't really tell straight from looking at it which one it is, right? Because all four of these will have carbon, all four of these will have hydrogen, and all four of these will have oxygen. So what we'll then do is we'll try to look at the general formulas of each of these and try figure out which one it or this specific example matches. Now, what do I mean by what do I mean by a general formula? That's very simple. It's what it's basically the formula that is used to determine any type of each a group, functional group. So there'll be a specific formula for aldehydes and ketones. There'll be a specific formula for alcohols, and there'll be a specific formula that will fit for all kinds of carboxylic acids, right? So let's go ahead and start off with heptanol. Um, Now, if you look at heptanol, like I said, all three of these will have um, will have carbon, will have hydrogen, and will have oxygen. Okay, it's a matter of which is which realistically. And for heptanol, well, let's start over here. Heptanol is an aldehyde, right? And the general formula for an aldehyde is CN, right? H 2N plus 1 and O and CHO, right? The CHO is separate from the other the other C's and the other H's, specifically for the fact that that is the functional group. Okay, that is the actual functional group that will determine whether or not it's an aldehyde. And if we just put this over here, okay, that's it for heptanol. We'll check now if it does in fact indeed satisfy that. For alcohols, we have CN, H2N plus 1, so very similar to the aldehyde. Let's try that one more time. And the difference is instead of CHO, you only have an OH. So that will be for both of these. Okay. And for a carboxylic acid, you will have C. Let's just try that one more time. The main difference with carboxylic acids is they will have two sets of oxygens. Okay, so CN, right? CN will have H2N, right? And you will have O specifically 2. Let's try that one more time. Yeah, there you go. Okay. And one of these definitely has to satisfy the molecular formula C7H14O2. Now, if you look over here, if you substitute in C7, 7 for N, you'll get C7, you'll get H15, so that already cancels out heptanol. It is definitely not an aldehyde. Let's try that again. It is definitely not an aldehyde. For the exact same reason, it will not be an alcohol. And if you look at the general formula for carboxylic acid, you will see that it, in fact, does indeed satisfy the general formula. So treating N to be 7, you have C to the 7, and 2N would be 14, which is what we see over here. And O2 is also satisfied. Props to you if you were able to identify the fact that carboxylic acids are the only functional groups or homologous series that will in fact have two oxygens within the compound. So if you had noticed that, well then props to you. You would have been able to correctly identify heptanoic acid right off from the beginning. Now, 1.2. Which one of the following structures is the functional group of an aldehyde? Now, the important thing about a aldehyde and really what separates it from the other singular oxygen groups such as alcohols and ketones is the fact that the aldehyde will have its functional group CHO all the way at the beginning of the parent chain, right? So a ketone will differ from that in the sense that the oxygen can be connected to anywhere within the the chain, right? And obviously the alcohol will need to have not only an O, an oxygen, but specifically a hydroxide, so an OH specifically. And the alcohol is none of these options because we see a double oxygen bond as opposed to an oxygen slash hydrogen bond, right? So all we need to do now is look through A, B, C, and D and figure out which one exactly shows a connection at the beginning. Yeah, a CHO connection at the beginning. Now, we cancel out option A simply because of the fact that this has two oxygens. And two oxygens is the hallmark of a carboxylic acid. We saw in question 1 over here that it is the only homologous series group that will have two oxygens. The other will either have one oxygen or zero oxygens, apart from an ester. Yeah, but we'll get to that in the one of the following questions. Okay, so A unfortunately is out. We can, oh, B looks promising. So you have a carbon, have it bonded to an oxygen, you have it bonded to a hydrogen, and by the looks of things, this should be in position number 1. So I will go and I will take a bet that the answer will in fact be B, but just to double check, let's look at all the other options. C cross out because again it has two oxygens, and D is the example of a ketone where it is connected, or where the carbon that carries the oxygen bond is connected to a series of other carbons on either side. So the answer definitely is then B. 1.3. Which one of the following equations represents a cracking process? Now, the process of cracking, very simple. You take a long carbon chain and you break it into shorter carbon chains, right? The important thing always to note, though, is the fact that you cannot lose any of either your carbons or your hydrogens, right? So if you started off with 40 carbons, your two constituents, or your two smaller constituents would both have to add up in terms of the number of carbons to what you had started off with. And likewise with the hydrogen, right? So again, 1.3, look at A, we have, let's see, 5 carbons, 6 carbons, and by the end of it, we will have 10 carbons, which is not exactly the case. If you look at B, or 1, 2, 1 plus 5 gives you 6 carbons, plus that extra 1 over there gives you 7. And that one over here gives you 8 carbons, right? And over here, 1 carbon, 7 carbons, 8 carbons. Okay, cool. It's promising. 8 carbons on the left-hand side, 8 carbons on the right-hand side. Now, let's look at the hydrogens. Three hydrogens plus 2 times 5 gives you 13 hydrogens. 14 hydrogens plus 2 over here gives you 16 hydrogens. So H2 gives you 18 hydrogens. And if we look over here, well, 3 plus 2 times 6 gives you 15, plus 3 gives you, in fact, 18 hydrogens. So on paper, this looks fine, okay? Number of carbons that we start with is the number of carbons that we end with. Number of hydrogens that we start with is equal to the number of hydrogens that we end with. The problem is, though, that this, in fact, is not a cracking reaction or cracking process. This is a different type of reaction in which you break a double bond, or you take an alkene and you add hydrogen to it to form an alkane. This is a different type of reaction. It is called hydrogenation. It is a type of, it is called hydrogenation, and it is a type of addition reaction. Sorry. And so, no, it is not a cracking process, even though the numbers do, in fact, work out. Now, let's look at C. One carbon, 7 carbons, 8 carbons, right? And over here, 1 carbon, 5 carbons, 6 carbons, 7 carbons, 8 carbons. Okay, the carbons all work out. Hydrogens, we have 3 hydrogens plus 2 times 6 gives you 15, plus 3 gives you 18. And over on this side, you have 3 hydrogens, 2 times 4 plus that 3 gives you 11 hydrogens. And these 3 give you 14, 15, 16, 17, 18. So on paper, it all works out. The numbers are fine. This is potentially what we're looking for. Now, what makes it actually the answer over here is the fact that you start off with a long chain, an alkane chain in this case, and it breaks off to give you a smaller alkane as well as a alkene. We start off over here with 1, 2, 1, 7, 8. We start off with octane, breaking off to give us 1, 5, 6, to give us hexane, as well as ethene. Right, so in actual fact, yes, this is our answer, 1.3 C. Right, let's move on to the next section. And like I said, we're going to read this twice. First, to understand which section we're in, and then secondly, to understand what it is exactly that we're supposed to do. They say the potential energy diagram for chemical reaction is shown below. Okay, now if you look at the picture, this falls under energy or thermal energy as part of a section, and they're basically asking us to analyze the graph and to answer the question about it below. Okay, now the question says, consider the following statements about the graph above. All right, and we are meant to figure out which statements above are true. Okay, and by the looks of things, it's going to be more than one statement that is true. In this case, let's see. X represents the potential energy of the products formed during the reverse reaction. Okay. By the looks of things, that is definitely true. Why is the X represented by the products of the reverse reaction? Well, if you look at this as the forward reaction, going in this direction would be the forward reaction, where you would have your reactants over this side and your products over here. But going in the reverse reaction, you would have your reactants in that case over on this side, and you'd have your products over on that side, which in this case would indeed be represented by X. So essentially what I'm saying is the reactants for the forward reaction will be the products for the reverse reaction. And so statement I is definitely true. Now, point 2 says the graph could be a representation of the change in potential energy for the following reaction. Okay, calcium carbonate breaks down to form calcium as well as carbonates in both in aqueous form. Right, and they say that because of this, we now know that the reaction itself will be endothermic because delta H is greater than 0, so therefore is an example of an endothermic reaction. What do we mean by that? Now, a endothermic reaction is one in which your reactants start off with less energy than the products. It's a reaction in which you take energy from your surroundings into the reaction, and you end up with a greater energy level at the end than you did in the beginning. A great example of this is you before you eat and you after you eat. Well, I mean, the process of eating makes or ensures that you end up with more energy at the end than you did in the beginning. And if you look at this, that's exactly what's going on here. You start off with less energy than what you end up with. So not only is 1 correct, but 2 is correct as well. And point number 3, the graph could be a representation of the change in potential energy for the combustion of methane. That is absolutely incorrect. And the reason why is a combustion reaction, all combustion reactions, are in their nature exothermic reactions, which means they give off energy to the surroundings as opposed to taking energy from the surroundings, which would be the opposite of what we see in this graph. In an exothermic reaction, you start off with more energy than what you end up with. And so statement 3 is definitely incorrect. And if you come down here to the options, that would lead you to A being the correct example over here. Right, then 1.5, they say a certain chemical reaction reaches equilibrium at 25 degrees Celsius. The equilibrium constant, Kc, for the reaction of this temperature is 1 times 10 to the negative 4. Well, after reading it the first time, you have probably correctly identified that we are dealing with a chemical equilibrium question over here. Not only that, but it definitely requires us to make use of Kc values. No problem. Let's see. Now we can read it a second time and understand what exactly they're asking us to do. So chemical reaction reaches equilibrium at that. The reason why they have to specify temperature is because, remember, the Kc value will change only in the difference. Only in the presence of a temperature change will the Kc value indeed change itself. Then they say the equilibrium constant for this reaction is a specific number 1 to the 10, 1 times 10 to the negative 4. Yeah. So, which one of these following statements regarding this equilibrium reaction is correct? Well, they say the concentration of the product is equal to that of reactants. That cannot be true, because if the concentration of the products was equal to that of the reactants, the Kc value would exactly be 1. Not the case. Okay. And just to remind you, actually, is the Kc value is equal to the concentration of products at the top over the concentration of reactants at the bottom. And if you treat this as a fraction, well, if the number is greater than 1, then that would mean your products are greater, or the concentration of the products is greater than that of the reactants. And if it is a number smaller than 1, but still greater than 0, then the concentration of the reactants would be greater than that of the products. So, I mean, by just looking at the question again, 1 times 10 to the negative 4 is definitely a number smaller than 1 but greater than 0. And so we're looking for one statement that relays the fact that our reactant concentration is greater than our product concentration. And that would be C. That would be C. The concentration of the products is lower than that of the reactants. The Kc value does not speak much of the rate of the forward reaction or the rate of the reverse reaction. It speaks only to the concentration of products and reactants. So not D, not B, not A, but C. Okay, then 1.6. Read it the first time. It's a chemical reaction at equilibrium question. So chemical reaction. Chemical equilibrium. And if you read it a second time, they say that this equilibrium happens in a closed container. Luckily for you, in this case, they have balanced the equation for you. But had they not, you would have had to balance it yourself, right, before doing anything in order to get your mole ratios, right? Then they say more HGO is added to the container at constant temperature. Then, how will the number in moles of oxygen gas, as well as the concentration, equilibrium constant, be affected at equilibrium? The Kc value, as well as the moles of oxygen gas, right? And by the looks of things, your two options for the number of moles is it either increases or remains the same, and your concentration, your in Kc either increases or remains the same as well. Well, if more HGO is added to the container, what will happen is the system will act in such a way as to try to decrease the concentration of HGO, right? Or will try to decrease the um, the amount of it. So in that case, we will have it be used up, right? We'll have it be used up, and in that case, actually, now let me look at it. Um, Start off with the Kc value, actually. So they say more HGO in solid form is added to the container at constant temperature. The fact that it's added at constant temperature would mean that the Kc value would remain the same. Now that cuts down our options um, to it either being B or C, right? It's either B or C, and the only difference really is whether or not the number of moles of oxygen gas will increase or remain the same. Well, given the fact that HGO is in solid form, the oxygen gas number of moles would actually not increase either, and you will have them also remain the same. So in actual fact, the answer would be C. Both will remain the same. Question 1.7. Okay, which one of the following solutions, each of concentration 0.1 decimeters cubed, has the highest pH? Okay, highest pH would be referring to which are most basic, right? So we can go ahead, we can cross out A because A is a strong acid and will definitely not be part of it. We can also cross out D, which is another form of an acid, in favor for either B or C. Now, in order to form B, we had ammonia, NH3, and we must have had HCl. Okay, strong acid, weak base will give you a acidic salt. In this case, C, we would have had NaOH, sodium hydroxide, and we would have had H2CO3, which would be a strong base this time with a weak acid, and so therefore we end up with a basic solution, right? And so therefore that's why C would be the answer. 1.8. The looks of things, reading it firsthand, it is a electrochemistry question. Reading it a second time, they say a cell notation for galvanic cell is given as follows. Which one of the following statements is correct for this cell? Okay, well, what you have over there is you have nickel forming its ionic form, and you have lead in its ionic form reacting to form solid lead. Okay, well, which one of these following statements is correct? Well, let's start over here. Okay, with Ni losing two electrons to become its ionic form, the act of losing ions or electrons is the act of losing electrons, right, is the hallmark of oxidation. Now, what I was trying to type over here is oil rig, which is a popular acronym standing for oxidation is loss and reduction is gain. Now, in this case, the nickel goes through oxidation because it loses its electrons, and lead gains electrons and so therefore is being reduced. And funnily enough, what is going through oxidation would be referred to as the reducing agent, and what goes through reduction is the oxidizing agent. So by the looks of things, nickel is the reducing agent because it undergoes oxidation, and lead is the oxidizing agent because it undergoes reduction. That crosses out C and D as possible options. PbS is reduced is incorrect because it's not Pb that is reduced, but the ionic form of lead is reduced, which leaves us with A, nickel is oxidized. There we go. And very quickly to finish off the multiple choice section, 1.9. Which one of the following combination correctly shows the products formed during the electrolysis of a concentrated sodium chloride solution? Quite a mouthful, but electrolysis is once again electrochemistry, this time of the electrolytic cell form. And if you read it a second time, they're looking for the products of concentrated sodium chloride undergoing electrolysis. Okay, well, sodium chloride would definitely either have sodium or chlorine, or in this case, hydrogen as a product, right? And in this specific case, the answer is B, because in the cathode, hydrogen would take preference over sodium, and in the anode, chlorine would be the other products that is formed, right? And then 1.10, which one of the following is not part of the eutrophication process? Well, that falls under the section chemical processes, right? And we're not looking for which one is, but which one is not part of the eutrophication process. Algal bloom is definitely part of the eutrophication process. Bacterial nitrogen fixation is not. I can circle that already, but just to double check, depletion of oxygen and water is definitely part of it, and the increase of plant nutrients in water is also part of it. So definitely 1.10, B is your answer. Yeah, and that section is just mostly going over the notes and understanding exactly what it is that makes up each process. Okay, so because of time and not in the interest of not making these videos too long, I will cut the first video here, and in the next video I will work through question 2, question 3, and possibly question 4. Cheers, see you in the next one.